Welcome back students. So today we'll continue with your previous pigeonhole principle. This is the second part to your previous PPT. We have already done up till example 5 in the previous one. So let's start with an example 6 over here. The t-shirts numbered consecutively 1 to 20 are worn by 20 members of a bowling team. When any three of them are selected to form the team, the sum of the numbers on their t-shirts is taken as the code for the team. Show that if 8 members are selected from 20 and from 8, at least one can form at least two different teams having the same code. Now solution goes like this. We have to select 3 members out of the chosen 8 members, and that can be done in 8C3 ways, that is 56 ways. So in total we are going to have 56 different teams. Now since the t-shirts are numbered from 1 to 20, the smallest sum possible over here is 1 plus 2 plus 3, that is equal to 6, and the largest sum possible over here is 8 plus 9 plus 20, that is 57. So in total there are 52 codes lying between 6 and 57, both inclusive. So if I take those 52 codes as pigeonholes and 56 teams as pigeons. Now if you can see, number of pigeons are more than the pigeonholes. That means by pigeonhole principle, at least two teams are going to have, two different teams are going to have the same code. So that is the result of that is the required result for this particular. So now let's see the next example, that is example 7. If 5 points are to be taken in a square of side 2 units, show that at least 2 of them are no more than 2 units apart. So I'll take this as a square. I divide the length of each side of the square is 2 units. I divide that square into 4 smaller squares of length 1 unit each. Okay. Now I go ahead and place the 5 points in it. First I place the 4 points, then the 5th point would definitely go to any one of the occupied square already. So that means 2 points are going to fall in the same square. Now the highest distance possible between any 2 points in this square is nothing but the length of the diagonal. Now if I join this diagonal and take this right angle triangle and apply the Pythagoras theorem, I'll get the length of the hypotenuse as root 2 because length of the sides are 1 each. So that is the highest distance possible between any 2 points in this particular square, and the same logic can be applied to any one of this square. So putting it in a verbal form, I take the square, divide it into 4 smaller squares of side 1 unit each, and I take those 4 smaller squares as 4 pigeons and the 5 points to be placed as the 5 pigeons. So number of pigeons are more than the pigeonholes, and therefore by pigeonhole principle at least 2 pigeons or 2 points are going to come to the same small square, and the highest distance possible between them is the length of a hypotenuse or the length of a diagonal, which turns out to be root 2 units. Next example, show that in a group of 50 students, at least 5 are born in the same month. Now, for a calendar year, there are total 12 months, so I take those 12 months as the pigeonholes and the 50 students as the pigeon. Now, again, if you can see, the number of pigeons are more than the number of pigeonholes. Therefore, by extended pigeonhole principle, we can say that at least 1 month is going to have floor of n minus 1 upon n plus 1, that is 50 minus 1 upon 12, floor of 50 minus 1 upon 12 plus 1, which turns out to be 4 plus 1, that is 5 students each. Next problem is, there are 30 dictionaries in a library containing a total of 61,327 pages. Then show that one of the dictionary has at least 2045 pages. If I take those 30 dictionaries as pigeonholes and 61,227 as the pigeons. Then by application of extended pigeonhole principle, I get at least one dictionary is going to have floor of n minus 1 upon n plus 1. Your n value is 61,200 and 327 and m value is 30. Substituting the values, I get a floor of that value is 2044 plus 1, which gives you 2041 pages. So at least one dictionary is going to have the list of 2045 pages. Next example, how many persons must be there in a group so as to guarantee that at least 5 people are born in the same day? Now, there are 7 days in a week. I'll take those 7 days as the pigeonholes, and I have to find n value, that is how many people are required so that in a day there are 5 people, at least 5 people who are born on the same day. So by extended pigeonhole principle, I have this, that is floor of n minus 1 upon n plus 1, and this value is given as 5. So using this and substituting the value of n over here, I get floor of n minus 1 upon 7 is equal to 5 minus 1, which is 4, which implies that n minus 1 is equal to 28, or n value is 21. So there should be 21 people so as to guarantee that at least 5 people are born on the same day. This is also an application of extended pigeonhole principle. This is the direct application of it. This is used so as to find what is the minimum number of people required so as to get a desired result. So we come back, we see the next example. If 6 numbers are chosen from 1 to 12 at random, find the least number of selection of 3 numbers that have the same sum. Now 6 numbers can be chosen from 1 to 12 in 12 C6, that is 924 ways, and the least sum possible of 3 digits taken 3 numbers at a time, the least sum possible is 6 and the largest sum possible is 3. So in total there are 33, the sum varies between 6 to 33, so in total there are 28 possible options for us. So if I take the 924 choices as pigeons and 28 possible options as pigeonholes, by extended pigeonhole principle I have floor of n minus 1 upon n plus 1, which turns out to be 33. So total there are at least 33 selections we have to be done so that we have 3 numbers, 2 different group of 3 numbers such that their sum is same. So next theorem we see that if kn plus 1 pigeons are kept in n pigeonholes where k is a positive integer, what is the average number of pigeons per pigeonhole? Now this can be done on an average, since there are kn plus 1 pigeons and there are n pigeonholes, on an average in particular pigeonhole there could be kn plus 1 upon n, which turns out to be k plus 1 by n. Now k plus 1 by n, k is an integer and n is also an integer, so 1 by n won't be an integer. So in short, k plus 1 by n is no longer a pure integer. So therefore at least one pigeonhole will contain the ceiling of k plus 1 by n, that value is k plus 1. So at least one pigeonhole will contain k plus 1 pigeon, and the remaining pigeonhole will contain k pigeons, which is nothing but floor of k plus 1 by n. That is the minimum number of pigeons which are required to ensure that at least one pigeonhole has k plus 1 pigeons is kn. Either you can use this result or you can use the theorem as it is. Now we'll see an application of this theorem. A bag contains 10 red marbles, 10 white marbles and 10 blue marbles. What is the minimum number of marbles you have to choose randomly from the bag to ensure that we get 4 marbles of same color? The solution goes like this. Applying the pigeonhole principle, if I take the 3 different colors, the n value will be 3, and on an average I should get 4 marbles of the same color. So I take k plus 1 value as 4. Solving this equation would give me k equal to 3. So the minimum number, now I'm applying this result. So the minimum number of marbles which are required so as to get 4 on an average of each color is nothing but kn plus 1. Substitute the value of k and n over here, which turns out to be 10. So you can see the elaborated result. The first 9 marbles will be like this: 3 red, 3 white and 3 blue, and the 10th marble could be any one of these 3 colors, any one of them, either red or white or blue. So in short, in total there will be at least 4 marbles of any one of these colors. So this is a question bank. You can go ahead and solve this. So with this we come to an end of this PPT. Thank you. Have a great time. You can always get back to me if you have any queries.